Greetings and welcome to Mr. Van Lowe's poorly monetized, low-budget science channel. Do not click like. Do not subscribe. All right, today we're going to take a look at topic 1.2 in which we propagate uncertainty. Your learning objectives. You'll note that this is the second lesson, and I'll put a card in here for the first one. Your learning objectives are to propagate uncertainties through calculations involving addition, subtraction, multiplication, division, and raising to a power. In other words, exponents. You will be able to explain what error bars do and why they are useful. You'll be able to define slope uncertainty, and we'll look at a couple of sample calculations as well. Okay, first, propagation of uncertainty. What are we talking about here? After we do some measurements, it's not unusual to do some calculations. So an example of this would be measuring mass and volume and then doing a density calculation, right? So our mass is going to have an uncertainty and our volume will have an uncertainty. And so our density, therefore, must also have an uncertainty. And finding the uncertainty of that calculated value is called the propagation of uncertainty through our calculation. Okay, so typically uncertainty is going to increase following a calculation. If your uncertainty goes way down, you might be a little bit suspicious. That can happen in some rare cases, but usually it's going to increase. Okay, so first let's look at propagation of uncertainty for addition and subtraction. So for addition and subtraction, you simply add together the uncertainties of each measured value. It doesn't matter if you're adding or subtracting. For the uncertainty propagation, you will add. Okay, so the data booklet has this. If y equals a plus or minus b, then the uncertainty of y will equal the uncertainty of a plus the uncertainty of b. So this delta here in each value signifies uncertainty in this case. Okay, so here's a quick example. A student is preparing an experiment. They need 235 milliliters of water. You only have a 100 milliliter measuring cylinder, and the student has to make 3 measurements. Okay, so those 3 measurements are going to look like this, where you've got 2 measurements with 100.0 milliliters, and our uncertainty is plus or minus 0.5 milliliters. And then our final measurement is 35 plus or minus 0.5 milliliters. Okay, so based on our previous slide, you might try to go ahead and calculate the reported value of the measurement, and I can wait. You'll just pause the video and go, or not. I'm going to do it in a second anyway. Okay, so your calculations should look something like this. Your volume, which I'm calling V sub 0 here, this would be the average volume or mean volume. This predictably is going to be 235.0 milliliters, and this is our calculated value. Okay, our uncertainty of volume is going to be the sum of our 3 uncertainties from each measurement. Okay, so that means our uncertainty is going to be 1.5 milliliters, and when we report uncertainty, we will round this to one significant figure. Note that there are some cases where you could go as many as 2 significant figures, but you will almost never be penalized just for rounding it off to 1 sig fig, and for the sake of simplicity, I recommend you do that. Okay, so we round this off to 2 milliliters, rounding up, because this is a 5, and you'll note that we've dropped our decimal place here. And the reason why we've done that is because our measurement cannot be more precise than our uncertainty, okay? So if our uncertainty is to the 1 place, then our average value should also be in the 1 place. If this were plus or minus 10 milliliters, then we would have to round it off to the tens. If this were plus or minus 100 milliliters, then we'd have to round it off to the 100th place, okay? So in this particular example, we're losing a significant figure due to repeated measurement. There could be some cases, however, with uncertainty where you could gain a sig fig. It's one of the advantages, I guess, of using uncertainty. Okay, so Ideally, you will measure one time when you're conducting an experiment. If you're measuring more than one time, then that's going to increase your uncertainty, and that's not ideal, okay? So don't measure more than you have to. All right, the rule for multiplication and division is going to look like this. So we're going to start straight off with a data booklet. If y is equal to a times b divided by c, then the uncertainty of y divided by the average value of y is going to be equal to what's called the fractional uncertainty of a, b, and c. So if you've watched my previous video, then you should recognize from the end of the video what these values are. Okay, so again, I will probably stick a card in here. Okay, so yes, as I just said, the uncertainty of y divided by the calculated quantity of y is equal to the fractional uncertainty of each term. Already said that. Okay, note that our fractional uncertainties are added regardless of whether our value is multiplied or divided. Okay, so division does not produce a minus sign here. Do not get confused. Again, we're generally going to tend to increase uncertainty and not decrease it. And again, recall just that delta here indicates absolute or possibly procedural uncertainty. Actually, I should probably change this. Okay, we can shuffle that equation slightly into what I think is a little more useful form, where we're just looking at the uncertainty of our calculated value y. So the uncertainty of y is equal to the calculated value of y multiplied by the sum of our fractional uncertainties. And we don't have to stop with 3 terms. We could have more than 3 terms, and that's why I have here delta n divided by n, suggesting that this would work for many, many terms. Okay, finally, to deal with exponents, we look at this scenario where y is equal to a raised to the nth power. Okay, so for our uncertainty, what we find is that the fractional uncertainty of our calculated value y will be equal to n multiplied by the fractional uncertainty of a. And this value can only be positive. We're looking at the absolute value. So if we have a negative exponent, we're going to drop that negative sign due to our absolute value bars here. Okay, I think I've already explained that point. So the rule for multiplication we demonstrated earlier would also produce exactly the same result. So exponents are a form of multiplication. Okay, next we're going to look at error bars. And I have here this graph, and you can see that there's a lot going on here. So we have y. So we've plotted y on the y-axis, and this is our average value of y. And then we have a line here showing the value y plus our uncertainty, plus y. And then we have the red line here, and this is the value of y minus the uncertainty of y. So we've got our plus and minus value here. We do the same thing on the x-axis, and I probably don't need to explain it. What you will note is that it produces this area, this box. And note that if we had to do this for every point, we'd have really, really messy graphs. It would look bad, and it would be very unclear. Okay, so what we do instead is we express our uncertainty using error bars. Okay, so here is that same box, but instead of plotting a whole bunch of points on here, we just have the error bar showing our uncertainty. And we know that our value, x sub 0, y sub 0, this point, could actually be anywhere inside this box. And that's what our uncertainty is telling us. So the advantage of error bars is that they're easy and clear and legible on graphs. They look great. See here, wow, that looks fantastic. So here's a scatter plot with error bars. And this was made using Logger Pro, and I'll probably throw a card in here for some of my Logger Pro videos as well. So you will be able to do this yourself. And this is not an unusual arrangement at all in physics. And generally speaking, you would just add a trend line right away. again, see the video to see how that's done. And this is really useful for analyzing data. And this particular trend line is going to give us velocity. Okay, so we have time on the x-axis and displacement on the y-axis. If we look at the slope of our trend line, what we're going to find is that the slope is given by a change in y divided by a change in x, and that is going to be displacement divided by time, which, as we know, is a velocity. So you can use this with all kinds of graphs, and whenever you look at a slope, you should be thinking about what that slope actually represents. Okay, so because we have these error bars on our graph, we need to look at what is called slope uncertainty. Okay, so what we do is we manually fit some lines. We have a couple of additional lines here. And what we're doing is we're setting a maximum slope and a minimum slope. Okay, so the maximum slope is going to be our steepest slope, and the minimum slope is going to be our shallowest slope. And note that Logger Pro here calculates the slopes automatically. So we have 2.350 meters per second for our automatic fit, and then our manual fit has these two other slopes. Okay, again, I'll throw a card in here so you can see the video in which I show you how to make a graph like this. So once we have our minimum and maximum slopes, then we can calculate our slope uncertainty, where our slope uncertainty is equal to maximum slope minus minimum slope divided by 2. And this looks exactly like procedural uncertainty, and you're going to find that this technique is extremely useful on internal assessments or individual investigations. Okay, so we're going to do an example calculation here. We're going to report the velocity shown on the graph with slope uncertainty. So the way that we're going to do that is pull our maximum slope right here and our minimum slope off of these manually fitted lines. And then our mean slope is from the linear fit. So this is just the average slope as calculated by Logger Pro. Okay, this should have a unit. Apologies. Okay, so to calculate our slope uncertainty, we're going to take those values, and again, this should have a unit, very annoying, and we are going to plug them into the formula that I showed you earlier. And what we're going to find is that our slope uncertainty here is equal to plus or minus 0.251 meters per second. And again, we'll round that off to 0.3 meters per second for one significant figure. So that means that our reported slope should be 2.4 plus or minus 0.3 meters per second. So we use the mean slope for 2.4, and we've rounded it off to the same number of decimal places as our uncertainty. We should not have more decimal places than our uncertainty. Okay, I've made that point, and again, note that you can add or remove potentially significant figures depending on the calculation. Okay, so our sources for this presentation are, of course, the Tsokos textbook, Physics for the IB Diploma. Great text. I've prepared it using Google Slides, LaTeX, Logger Pro, Adobe Illustrator, and PD Expert, and a partridge in a pear tree. This has been Mr. Van Lowe's poorly monetized YouTube channel. Do not click like, do not subscribe, but do have a wonderful day.